So my name is Jordi Farrés, and I work at the European Space Agency since more than 20 years. And today I'll be speaking about our strategy towards cloud computing and also how OpenNebula helped us doing that. But I think before I should explain a bit what is our job, what is our objective, and share that with you. I don't know if you already know what is the European Space Agency. I'll just say very briefly, it is an organization formed by 20 member states. It is not part of the European Commission. And even one of the member states, the associated member states, is Canada. So it's not quite European. It has a budget of about 4 billion a year and performs activities on a number of areas like launchers, astronomy, telecommunications, navigational systems, space security, basic technology, human flight and exploration, and Earth observation, which is the directorate I work for. Earth observation is the biggest program in the agency. It's the one which flies more satellites. It's the one which has more budget, and it's probably the most useful one, as normally watching the Earth provides normally better source for new applications for social development than maybe some of the other programs. I myself work in the R&D group at the ground segment, Earth observation ground segment. Ground segment in our terms means all the processing, downstream processing of the data we are receiving from the satellites, which by the way is the film some of you were watching just before my talk. Okay, so today I will basically briefly introduce what our objectives on cloud computing and try to explain also why some of our objectives may be not so common. And then we'll go through a number of projects that illustrate how we have tackled this objective on different moments in time. These projects are just a selection of projects. I have selected them because they illustrate the different objectives, because all of them used OpenNebula somehow, and because I manage all of them. Okay, so but does many more things on cloud computing as well. And after that, we'll then derive what's been the lessons learned and what is the path, our roadmap in the future regarding cloud computing. So by looking at the objectives, I think some objectives are very common. The reasons why people move to cloud computing are typically in this list. ICT cost savings, it's usually one coming first. Dissemination, peaks, processing bursting. But also in our case, very much also collaboration. Okay, I will go a bit one by one. Dissemination, peaks, and processing bursting. We in our sector typically serve data-intensive research activities. Data-intensive research activities that require high processing capabilities and dissemination capabilities, typically at badly distributed over time. There is normally peaks related to events on Earth, like geohazards, disasters, volcanoes, this type of things, which require significant increase of resources. And for that, of course, cloud computing looked as a very interesting solution to address this peaking. Also, the collaborative aspect is very important for us because the agency is an agency, so we typically try to meet the offer in demand, meaning we try to deploy satellites that can serve specific research activities, specific applications, scientific disciplines, but somehow very much our purpose to get this data, these new possibilities exploited by society, by research. And that means very much promoting collaboration across scientific institutions, service providers, and also policymakers. For that reason, we frequently want to push a bit this together, and we also thought the cloud computing was a medium where this could be attained. Just to give a bit more substance, I have just put one slide on our background. This is the ESA convention, and I'll just highlight that the role of ESA, if you read there, is about promotion, collaboration a lot. So sometimes our role is not so much to do things, but to give incentive for others to do things. And many of them are related to also the evolution of industry in our member states, so that their space sectors are competitive and are at the top. For that reason, I have included also a fifth objective, because we think that this technology improves the capacity of our industry in being effective, and so we also have picked up an objective, which is the promotion of cloud computing among our industrial space sector. This is not so different from what we did maybe 20 years ago, when I remember we were really encouraging our companies to move to internet, to move to business, and so on. And okay, now it's obvious, but at that time certainly it was not obvious. When you ask somebody in their financial department of Astrium in Friedrichshafen to connect to internet, was like a shock. Okay, so now we'll move to these few experiences. I have selected 4, and they are exposed also chronologically. So the first one, it's a mass processing activity we perform on Amazon, and we keep also performing, I must say. This was back in 2009, and the emphasis was set on the volume. So had to be fast, had to be large. So we selected a very specific type of data. It was radar data, but also atmospheric data of a certain size. It was, in the case of atmospheric data, which was about 8 terabytes of data that we wanted to process. So that was performed using 200 virtual servers that were federated to our grid computing. So we could easily deploy our application on Amazon and run it. It was run on 5 weeks, but the CPU was equivalent to 11 CPU years of processing. So that was very much a success. So just for you to give you a flavor of what this meant, it basically this instrument is it's measuring the ozone layer at different heights, and by having the full time series, you can see how the ozone layer over Antarctica develops at the different heights. So what were the the observations of this project and the conclusions. So on the first, the experience was successful. The processing capabilities were provisioned very easily, and the processing produced the expected results on a good time for our scientists to work on them. In this case, more than our scientists, was our quality services that had to somehow validate this new application. This very first exercise obviously was very much aimed to check the cost effectiveness of the cloud, and that was not so easy to confirm because the price of the cloud changes, and we were lucky, for instance, to use free data upload during our activities, because at that time they decided that for a few months it was going to be free. As soon as we publish our results, the prices change again. So it was quite difficult for us to respond to the question of how much it costed, how much you have saved, and so on. Of course, for this type of activity, the bottleneck is the staging of the data on the cloud. We tried different approaches, staging the data via hard disk and having most of the data processed the most quickly possible with the maximum number of machines was in the end the cheapest. We also tried online transfer and processing on the fly, but that was typically taking longer and in the end being more expensive. So we really were quite happy with sending our hard disk to Ireland for this activity. Oops. Yes, of course, as I said, the faster the cheaper was one of the conclusions. We, of course, at that time had ad hoc scripts to command the provisioning that we soon replaced by Gridway and now by OpenNebula somehow. Of course, we also somehow took advantage of the fact that these applications had been in the past gridified, and what we did was to deploy basically computing element of our grid on the provision machines of Amazon, and that did not require changing the application or addressing other topics that would have been more difficult. Of course, we were a bit we were in the world of Amazon, which is quite specific. So that was the first experience. Then we decided to do something else, to put the emphasis somewhere else. So one of the weak points of Amazon was the cost and the staging of the data. So we tried to have a second project where staging was not going to be a problem, because we basically coupled processing services with dissemination services. So the data was going to be persistently stored on the cloud. And also we tried to address the cost by resorting to low-cost hosting services. We used a company called Hessner for that, which is based in Germany. In this case, the data that we used was radar data. Radar data is very interesting because it allows to detect small changes on the ground. Small changes on the ground that could be useful to assess damage after earthquakes, or could be useful to monitor extraction activities like oil or water, because the terrain goes down when you extract. Or also for urban planning, it is a very useful technique, because you can detect areas which are not so solid as they look like, and you may decide where to build or not to build. especially if you build power plants and things of this type. So this data, it is high interest also by in the commercial sector, but it requires a lot of processing as well. So this is just one example of the kind of data and timing that you need in order to have this time series analysis on the subsidence of the terrain, for instance. So in this case, what we did was to make the data available on the cloud, but also to configure it in such a way that the cluster was serving the data for dissemination. At the same time, the same cluster, it was configured as a Hadoop cluster and could execute the processing on demand. So also here we had some analysis of the results. The scalability of the solution was reasonable. We basically, in this case, used traditional hosting service by the provider on dedicated servers, and we were increasing these servers one by one, depending on the amount of data and processing we needed. It was basically on a granularity of 8 terabytes at a time. The cons was that we somehow coupled dissemination and processing on the same servers, and of course, these things do not necessarily need to scale together. I mean, the demand could be more on processing than dissemination, the contrary. So our solution was not so good in that sense. The synergy of, on the other hand, the synergy of processing services and dissemination was, I think, very well received in our organization, because obviously it put aside the problem of taking the data to the cloud. You make already an effort to have the data that is mostly which has more interest for the users already in the cloud. Of course, the prices were quite lower with respect to Amazon, but also with respect to CDNs, content delivery networks we had used in the past, like level 3. And of course, the service was not to that level in any case. In this case, we rented hosting, so it were dedicated servers, and that also is some of our discussions on security at the internal visa. On the other side, it forced us to manage by ourselves the virtualization layer and OpenNebula, which first was not laid down, but later it was laid down. By the way, all this work was done by TerraDuve Manuel, which is sitting there. So we can also have a more technical discussion later on. So then we moved to another project where we try to put emphasis on another 2 aspects. One was the multi-sourcing, and another one was the collaboration, the collaborative benefit the cloud could provide to us. And this project was hosted on a number of providers, cloud providers, that associated in this so-called Helix Nebula initiative. And so we were hosting this project on Atos, Cloud Sigma, Interroot, and T-Systems, all commercial, but also at the very last, also EGI joined, and so we could also host it in the Fed Cloud. We'll see in a moment, but because these different providers have different APIs, different management systems, you cannot get something done once to suit all. We had to we were somehow pushed to use cloud brokers. We used two, Slipstream and Stratius. Two, because the different cloud providers had different preferences, and eventually we had to use two. The data that it was used in this case and the applications is very similar to the one I explained before. So it was also radar data, which has all these potential use for earthquakes, for also floodings, because you see radar sees water very well, and also these other applications I was mentioning before. In this case, we were using a data set of around 15 terabytes of raw data, and that was coupled with a number of applications. I'm sorry, we call them processors, which is an overloaded name. A number of applications that allow the users to use this data. So here we are trying to put also the emphasis on collaboration, and I just explained with this slide a bit what we meant by that. We coined this concept of exploitation platforms. Exploitation platform meaning a medium where we fit data, software, and ICT resources, and where our users can go and develop their scientific activities or their services. But it's not only that, because you can also close the loop and get these services to enrich the platform. And of course, it's this recursion loop that give the power to the concept, because it means that what you are placing on the cloud will grow by the activity of the users of the platform. And this concept, we still believe on it. In fact, it's in one of our strategic initiative now. I must say that in this project, the loop was not closed. So we put a number of services, a number of ICT resources from all these cloud providers I mentioned. We put software, and I will in a minute mention all the problems with that, with licensed software, for instance, and data, and we got users, but still we have to close the loop and get the services to be deployed by the users themselves on the same platform. This is how the platforms look like. So the users normally connect to the platform by using maybe a virtual machine, which is kind of desktop. And on that desktop, they can see basically the mechanism to access the data, which is, of course, co-located on the same cloud where the workstation, the virtual workstation is running, and also the different applications, some of which are licensed applications the users can use on this data. So altogether then look like this. When they start opening the applications and accessing the data and all that. We also conducted, I just mentioned it at the beginning, not only with these commercial cloud providers, but also with EGI, that it's also a member of Helix Nebula. And in that case, the trial was done with these three resource providers, which belong to the EGI. For us also was very interesting, because it allowed us to experiment the performance with scientific institutions that provide cloud computing services in new member state countries like Czech Republic, Greece, and soon Romania. So in this case, the experiment was successful from a point of view of performance, of the the solution provided by the cloud providers. Not all cloud providers were at the same level. Many were going through upgrades of their middleware, of their capacity. Some of them, we had the impression that they were plugging in resources as we were trying to use them. So not very mature services, far from Amazon. A problem we had somehow, because we were using this multi-sourcing approach and trying to locate data and processing activities on different providers, we of course had to couple these two. The connectivity, inter-cloud connectivity, was very poor, and is one of the subjects that Helix Nebula is addressing at the moment. I think they're trying to solve it by getting high connectivity with GEAN. The use of also of the different cloud providers was not easy. They are not speaking the same language, not using the same technologies, not using the same models, the same costing models. It's all a bit different in each of them. We of course asked them to federate and to provide a common interface, and they ask us to go through by a broker that will do that. But the brokers are also not mature, at least the ones we tried, and so it's been a bit of a pain. We also, in this project, and for the first time, allowed our users to provision virtual machines by themselves. Basically, the machine that I was showing to you, that was a kind of workstation, had been designed to serve this type of community. They can provision by themselves. It is not, they are not accessing the OpenNebula console. It is, they are going through a small request that we need to approve and serve them. It's quite simple interface for them to provision these resources. We are now working very much in allowing them to provision different type of appliances. So not only workstations where they can use these tools they already know, but also specific appliances specialized for cluster processing of the data, etc. A problem we had there was on cost licensing. Typically, these users use specific languages like IDL from Excelis, applications like Gamma from Gamma Software in Switzerland. These tend to be expensive costs, and so it was for them also a good motivation to move to the platform, because they didn't need to buy a license. They would get a license on our on these workstations, virtual workstations we're providing. The pain was for us to get agreements with the vendors to release these licenses on the cloud. None of them had a clear policy on how to license their software on the cloud. And I think there is a lot to do, and a lot by ESA to do, so that this thing is really starts to move well. Again, as we had done already at the beginning with Amazon, the deployment of applications was relatively simple, because we always were using applications that had been gridified, and so we're using always the grid as a computational framework to run on the cloud, or the workstation. So some software was running, desktop software were just installed in these virtual workstations that were given to the users. We were, I put it as a cons, we were also expecting a bit to move to a more native cloud computing paradigm. In particular, we're expecting to move to MapReduce, but we'll see, that's a bit the next project. We were not doing that there. So the last one, The last one at a different emphasis was very much to provide the users the capability to close the loop I was mentioning at the beginning. So the possibility by users to develop the services that then we can also release on the platform so that they can enrich the platform. They could, if the services are valuable, generate revenue from that. So typically, this is a bit the scenario that was envisaged. There are many data sources and many users, and by placing the cloud in the middle, you'd expect that there is a wealth of service providers, of companies that make business on this context. So there's a bit, to enable that, we had to somehow create a model through which users could develop their own services and deploy them on the cloud. So, okay, in this case we used hybrid cloud because the development platform was very much sourced by our private cloud and the public cloud for the deployment and the use of the developments of the services that had been developed there. As we were using still some of the cloud providers of Helix Nebula, we had to develop the specific drivers for T-Systems, for Interroute that we release, or we are releasing on the OpenNebula distribution. We also had the deployment model. I mean, what are the services that the users may develop and deploy by themselves? So we consider both the services package as appliances, so that the service which is developed becomes an appliance that is available in the catalog of appliances, and users can request it and run it on their own accounts, or software as a service, which basically in our case was web processing services that we make available to the users for the processing of the data. In this case, this is very much done on our own, because the cloud providers are concentrated still on infrastructure as a service, and they have not much for PaaS or SaaS. We also promoted then the development of services using MapReduce and Hadoop clusters, and this, of course, it is requires the applications to be developed on this platform, which means it is a slow process because it requires the applications to be designed for that or to be ported to that platform. So this is slow adoption. So these are the 4 cases that I was planning to explain. I will just mention very briefly on a slide a bit what was the role of OpenNebula in each of them. So for the first one, basically the one on Amazon, we were not using OpenNebula at that time, but we used the Gridway, which was kind of predecessor of OpenNebula by the same team of Ignacio Llorente, and now we are also using OpenNebula with Amazon. On the second one, we used OpenNebula to host our private. I mean, we had to layer this virtualization layer on top of the machines that we were being provided by Hessner. So it was kind of private cloud in the rented machines. On the third one, we've seen that we didn't use it directly, but it was used by some of the resource providers. We've seen that in particular those federated to EGI were employing normally OpenNebula. And on the fourth case, we used OpenNebula to set up the hybrid cloud that was serving as development environment for the service providers to develop the services, and then through the drivers that I mentioned before, the deployment of these services on T-Systems, on Interroute, on some of the commercial cloud providers. Okay, so now we move a bit to what are the main lessons we learned from that and how that is now defining our roadmap. So I will mention 4 lessons. So there are many more, but I will stick to 4. And the first one is that we want to do hybrid ICT provisioning, and the reasons are 2. Basically, one is economical. Normally you have highs and lows, and of course if you use your own infrastructure for your fixed demand and use the cloud for the peaks, it is going to be probably cheaper than moving everything to the cloud. And also, of course, it is more convenient as a transition, because you start by already having normally a large data center, and you don't want to close it the day after. So I don't think this is a very surprising lesson. The second lesson concerns the multi-sourcing. We really recommended multi-sourcing for several reasons as well. One is typically the terms and conditions, the SLA you get from the cloud providers are not brilliant. So in order to mitigate the risks of a cloud provider disappearing or merging or whatever, I mean, there are many things happening in this market, to use multi-sourcing and to have contingency plans in case you want to migrate from one cloud provider to another, or in a short notice. That means basically that you need to keep also in-house a certain amount of capabilities and data to do that. The third lesson, maybe not so relevant in this forum, because the third lesson concerns what is the functional footprint, what we are recommending to our management to place on the cloud or not. So in our case, and I mentioned already that the fact we have these dissemination peaks, we have these processing peaks, we have typically 2 copies of the archive. We have a secondary archive which is used in case of problems with the primary archive and so on. So there are a number of functions that are typically flexible on demand. The volumes can change very quickly, and for all those we recommend it to go to the cloud. But what is more interesting is that these functions are synergetic. So the fact that, for instance, I was mentioning before, the fact that you have the data persistent in the cloud to serve your customers and disseminating the data allows also to serve the processing peaks with that data on the cloud. And the same goes for the secondary archive. So we are encouraging this the migration to the cloud of these functional areas. The fourth and last lesson learned, it concerns the user expectations. So it is not so technical. Our users, as I said, are scientific research users, but also service providers. And they have very high expectations. I think that was already mentioned by other speakers. They would expect that our data is available online all the time at high speed, that they can access it for free, and that also it is arranged in a coherent and easy to use manner, that they are able to process this data very much on their preferred cloud provider or on their own premises if they have enough capacity, that they can resort to open source software to process this data. At least a good basis of the software should be open source, and also that we provide means for open collaboration, meaning in particular what I was saying before, that the efforts done by a company are capitalized into new services that can be deployed through the same platform and multiply the results of the community. And of course, our recommendation is to be up to the expectations. Okay, vis-a-vis OpenNebula, regarding the lessons learned, I think that, of course, it had a nice match for some of them because we used already OpenNebula on our hybrid cloud. We used OpenNebula to implement the multi-sourcing through all these drivers I mentioned. And of course, also OpenNebula, being open source, matches very much the expectations of the research community. It is really important when you serve researchers and academia that the solutions you propose to use them on your platform are solutions they could deploy by themselves in their own resources at low cost, because this is a matter of trust. They may never do that. They may always keep using our facility. Still, they know that they are using software there that they could at any time install on their own facility and run it as they run on us. This is important. And so in that sense, OpenNebula, it is very aligned to this. Okay, so now I move to the future prospects, so that will be short. So these are very much the recommendations. There is now an action to put that on a white paper to, I think we'll go to SciOps level, which is this UN body where all the space agencies in the world meet. And this would be a bit, well, these are my proposal for this white paper. We'll see what comes out in the end from the white paper. But very much first is to set up a midterm relation with a few cloud providers with the aim to have multi-sourcing, but also to mitigate the risks I was mentioning before. We, in particular, have chosen to typically couple that with our networking providers, because that also facilitates the problem of data staging. We, of course, started and have to complete the cloudification of the present corporate computing resources, and then establish an hybrid cloud, probably managed in-house, not through the hybrid services that some cloud providers propose. Then we also recommend to establish clear policy on which applications and which services should be provided from the cloud. And in particular, our recommendation is for services like integration, validation, demonstrators, R&D, but also to promote the use of cloud computing among our service providers. Remember, ESA buys more than does, and that means that we place large contracts to our service providers to run our facilities, and frequently it's their choice to use cloud computing or not. We have to favor them move in that direction. And of course, continue running flagship projects that illustrate the benefits. In particular, a thematic exploitation platform that we are launching next year with a budget of 6-7 million. We also recommend ESA and other space agencies to really promote open data policies. ESA is recently adopted open data policy for the new generation of satellites, and this is nicely coupling also with open source, we see. The adoption of and promotion of interoperability standards at different levels, typically in order to access the data, to use the data, to discover the data, but also in the area of authentication, authorization, to promote open source software, in particular in the area of Earth observation data processing, and promote open computing, meaning cloud computing paradigm with open standards so that people can really choose one cloud provider or maybe another, or maybe their own internal cloud without having to big problems on migrating applications or licensing. So, last minute, the manifest. And this is really the message, is that the putting together open data, as we do, open source software to exploit this data, and a computing paradigm that can be served by many suppliers in a seamless way, really offers a lot to this sector, to the space sector, but I would say it's also true for many other sectors to develop, to be more effective, more competitive, and better for society. Thank you. There are a number of reasons why different directorates, different programs in ESA use different technologies. It is linked to the way that ESA is financed and programmatically structured. I hope that with the issue of a white paper at CEO's level, which is the highest level we can go, which involves all of ESA activities and also other agencies, airspace agencies, this could be addressed. I was mentioning as one of the aims is to promote standards. We typically have deployed and developed the standards which are more specific to space, to how to format the data, how to access the data, how to discover, how to organize the catalogs, interoperability and catalogs. But I am also for promoting standards in the sense of at least guidelines on which type of API we should use for the IaaS provisioning. I am for it, but I don't have one. The end users don't see what is the API, what is the standard being used behind. What he sees, of course, is the possibility to migrate his service or to resource his service from one provider to another, which of course it is a really important point when the market is not so mature and you may be using a cloud provider today that may be convenient for you, but you don't want to be locked because the market could well evolve quickly and you lose your provider. Or the provider migrates technology, which I've seen also that. And all of a sudden you have to migrate.